Now here the question is, show that this integral from 0 to infinite e to the power minus alpha x into sine beta x upon x dx is equal to tan inverse beta upon alpha when alpha is greater than or equal to 0. And then from this result we need to deduce that this integral sine beta x upon x will be pi by 2 if beta is greater than 0, 0 if beta is 0, and minus pi by 2 if beta is less than 0. Now here we have this function which has two parameters, alpha and beta. So we write this function as f alpha beta, and it'll be this integral from 0 to infinite e to the power minus alpha x into sine beta x upon x dx. Now what we'll do is we'll differentiate this function partially with respect to say beta. So we'll write del f upon del beta. It will be this integral from 0 to infinite e to the power minus alpha x upon x, and then derivative of sine beta x will be cos beta x into x dx. Now here x and x will cancel. So we are getting this del f upon del beta as this integral from 0 to infinite e to the power minus alpha x into cos beta x dx. Now this is a standard integral which we solve using by parts. So here I won't solve it, I'll use the result directly. So we'll write del f upon del beta, and L be equal to e to the power minus alpha x upon alpha square plus beta square, and then minus alpha cos beta x plus beta sine beta x from 0 to infinite. Now when x is infinite, it will be e to the power minus infinite, which is 0. So we write del alpha upon del beta, and if we put upper limit, this entire function will be 0, and then minus lower limit. So we'll put x is 0, e to the power 0 is 1 upon alpha square plus beta square, and then minus alpha, cos 0 is 1 and sine 0 is 0. So we'll write del f upon del beta, and it'll be alpha upon alpha square plus beta square. Now we'll integrate this function with respect to beta. So we'll get f alpha beta, and here will be this alpha, and then dx upon a square plus x square will be 1 upon a tan inverse beta upon alpha plus c. Now here constant, it can be some function of alpha, so we'll write this as some c alpha. Now here alpha and alpha will cancel, so we'll write f alpha beta, it will be tan inverse beta upon alpha plus c as some function of alpha. Now we need to find initial conditions. If we put beta as 0, we'll get f alpha comma 0, and then here we'll have sine 0. So value of f alpha comma 0 will be simply 0. So we'll use this initial condition. So if we put beta is 0, here L be 0, tan inverse 0, L be 0, and then plus c alpha, that means value of this constant is simply 0. So f alpha comma beta will be simply tan inverse beta upon alpha, which is the result that we need to prove. Now using this result, we have to deduce that this integral sine beta x upon x dx will be this function. Now if we look at this integral, we know that we do not need e to the power minus alpha x. So what we'll do is we'll simply take limit alpha tends to 0 both sides. Now if we take limit alpha tends to 0, it'll be e to the power 0, which is 1. So we can write this integral from 0 to infinite sine beta x upon x dx, and it'll be this limit alpha tends to 0, tan inverse beta upon x. Now value of this limit will depend on beta. If beta is less than 0, it will be tan inverse minus infinite, and tan inverse minus infinite will be pi by 2. In that case, value of this integral will be minus pi by 2. Now if beta is 0, in that case it will be tan inverse 0. That is, the value of this integral will be 0. And if beta is greater than 0, it will be tan inverse plus infinite. Then the value of this integral will be plus pi by 2. So this integral from 0 to infinite sine beta x upon x dx will be pi by 2 if beta is positive, minus pi by 2 if beta is negative, and will be 0 if beta is 0.